Have you ever wondered what the universe looked like in its infancy, just a few 100 million years after the Big Bang? How can we see events that happened billions of years ago? The answer lies not in a fictional time machine, but in the light itself from the most distant objects, quasars and early galaxies. Imagine brilliant lighthouses shining across billions of light years to reach us, carrying messages from a young, violent, and mysterious universe. These ancient lights are not just bright spots in the sky, they are living evidence, rare snapshots of the cosmic dawn, revealing how the first galaxies were born and supermassive black holes formed. Let's explore the mystery behind these cosmic lighthouses. Welcome to SpaceTime's journey of cosmic exploration, where we delve into the deepest mysteries of the universe. In this video, we will explore quasars and distant galaxies, along with evidence of the early universe. Don't forget to subscribe to our channel so you don't miss out on other exciting cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us. To truly understand the early universe, we must look into the past. Fortunately, the universe itself is a colossal time machine, constantly revealing its oldest secrets through light. Light with a finite speed of approximately 300,000 kilometers per second carries precious time traces. This means that when we look up at the night sky, we don't see stars and galaxies as they exist right now, but as they existed in the distant past. For instance, light from the sun takes about 8 minutes to reach Earth, so we always see it as it was 8 minutes ago. With the nearest galaxy, Andromeda, we see it as it was 2.5 million years ago. And when we point telescopes at extremely distant objects like quasars, we are traveling billions of years back in time, all the way to the very infancy of the universe.
Quasars, short for quasi-stellar radio source, are the brightest and most distant objects we can observe in the universe. Initially, they were discovered in the 1950s as powerful radio wave sources. However, when scientists tried to observe them with optical telescopes, they only appeared as faint pinpoints of light resembling ordinary stars. It wasn't until their light spectra were analyzed that scientists were stunned to realize they were not stars, but objects with enormous redshifts, an unmistakable sign of their extreme distance. The concept of redshift is the key to unlocking the door to cosmic history. This phenomenon is similar to the Doppler effect in sound. The sound of a fire truck sounds higher-pitched, high-frequency as it approaches, and lower-pitched, low-frequency as it moves away. For light, when an object emitting light moves away from us, the wavelength of that light is stretched, shifting towards the red end of the electromagnetic spectrum. Conversely, if the object moves closer, the light shifts towards the blue end. Astronomer Edwin Hubble was the first to realize that most galaxies exhibit redshift, proving that the universe is expanding. Importantly, the farther away a galaxy is from us, the greater its redshift, meaning it is moving away from us faster. For quasars, the redshift is astonishingly large, indicating they lie at the furthest edges of the observable universe. This means that light from them has taken billions of years to reach Earth, carrying an accurate image of the universe when it was very young, only a few 100 million to a billion years after the Big Bang. By studying the light from quasars, scientists can gather information about the physical conditions, chemical composition, and even the expansion rate of the universe during those early moments. They are living evidence, the oldest witnesses to the harsh and dynamic conditions of the early universe.
So what exactly are quasars that they can emit such enormous energy, capable of shining across billions of light years, far outshining hundreds of billions of stars in a normal galaxy? Modern science has determined that quasars are extremely luminous active galactic nuclei powered by supermassive black holes located at their centers. Most large galaxies in the universe, including our own Milky Way, harbor an SMBH at their core. However, while Sagittarius A star, the black hole at the center of the Milky Way, is relatively dormant and only consumes a small amount of matter, The black holes in quasars are actively and fiercely devouring colossal amounts of material. When matter, including gas, dust, and even stars, is drawn in close to a black hole by its immense gravitational pull, it doesn't fall directly in, but instead forms a gigantic swirling structure called an accretion disk that orbits the black hole. The matter in this disk is compressed and heated to millions of degrees Celsius due to internal friction and extremely powerful gravitational forces. At these incredibly high temperatures, the matter emits electromagnetic radiation with astonishing intensity, spanning the entire electromagnetic spectrum, from radio waves, infrared, visible light, ultraviolet, X-rays, all the way to gamma rays. It is this extremely powerful and concentrated radiation from the accretion disk that creates the characteristic brilliant luminosity of quasars. The existence of such colossal supermassive black holes, with masses up to millions, even billions of times that of the Sun, in early quasars just a few 100 million years after the Big Bang, remains one of cosmology's greatest mysteries. How could they have formed and grown so rapidly to such immense sizes in a relatively short period? Scientists are considering several hypotheses, including the possibility of larger initial black hole seeds formed from the direct collapse of gigantic gas clouds, or an extremely rapid accretion rate in the younger, denser cosmic environment. Not only luminous quasars, but also the first galaxies provide valuable evidence about the early universe and the process of structure formation. Before the widespread emergence of quasars, the universe went through a cosmic dark ages, lasting several 100 million years after the Big Bang. During this period, the universe cooled enough for electrons and protons to combine into neutral hydrogen and helium atoms, making the universe opaque and impenetrable to light. Then, approximately 150 to 800 million years after the Big Bang, the first stars and galaxies began to form, emitting powerful ultraviolet light. This high-energy light reionized neutral hydrogen into plasma, making the universe transparent and allowing light to travel freely. This crucial phase is known as the epoch of reionization. Quasars played a significant and profound role in this reionization process. The enormous radiative energy from their accretion disks, along with light from billions of newly formed stars in early galaxies, provided enough energy to ionize a large amount of hydrogen gas in the intergalactic medium. Studying the light spectra from distant quasars can tell us about the ionization state of hydrogen in the universe at the very moment that light was emitted. Characteristic absorption lines of neutral hydrogen in quasar light spectra allow scientists to measure the extent of the universe's reionization at different times, thereby painting a picture of the progression of this crucial process.
The early galaxies we observe are often very different from the modern galaxies we are familiar with. They are typically smaller, irregularly shaped, and lack clear spiral or elliptical structures like mature galaxies. Notably, they are forming stars at an incredibly rapid rate, hundreds, even thousands of times faster than the Milky Way today. The early universe was a chaotic place, where galaxies constantly collided and merged, fueling explosive star formation. The first stars were formed primarily from hydrogen and helium, lacking heavier elements. When these colossal stars died in spectacular supernova explosions, they created and dispersed heavier elements into space, laying the groundwork for more complex generations of stars and planets later on. With the advent of the James Webb Space Telescope, JWST, our observational capabilities have been pushed even further to an astonishing degree. JWST, with its infrared vision, can penetrate the dense layers of dust and gas in the early universe to detect light from extremely distant galaxies and quasars, providing an unprecedented detailed view of the epoch of reionization and the formation of the first cosmic structures. Images and data from JWST are revolutionizing our understanding of the dawn of the universe. Before quasars and early galaxies began to shine brightly, the universe underwent another crucial formation stage, the greatest evidence of which is the cosmic microwave background. The CMB is the oldest remnant light from the Big Bang, appearing approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely. Quasars and early galaxies, although appearing later than the CMB, fill the gap immediately after that event, providing a continuous picture of the universe's evolution from its very first moments.
While the CMB tells us about the initial state of the universe, a relatively homogeneous and hot universe, quasars and galaxies show us the dramatic transition from a uniform universe to a complex, structured universe, with galaxies, galaxy clusters, and superclusters as we see them today. The distribution of quasars and early galaxies in space and time helps scientists map regions of matter density in the young universe. Through this, they can test cosmological models of large-scale structure formation, from initial quantum fluctuations in the very early universe to the formation of colossal structures. Another important tool used by astronomers to study these distant objects is the phenomenon of gravitational lensing. According to Albert Einstein's theory of general relativity, matter and energy warp spacetime, and light traveling through that warped spacetime will be bent accordingly. This means that massive galaxies or galaxy clusters located between us and a distant quasar or galaxy can act as a natural gravitational lens. This lens not only deflects the path of light, but can also magnify and sometimes create multiple images of the same distant object. Gravitational lensing allows us to observe quasars and early galaxies that would otherwise be invisible because they are too faint or too small for current telescopes to resolve. By studying gravitationally lensed quasars, scientists can not only accurately measure the mass of the galaxies and galaxy clusters acting as lenses, but also obtain more detailed views of the magnified objects at extremely high redshifts. This is a powerful technique, especially when combined with next-generation telescopes like JWST, helping us to overcome the limits of existing technology and explore the deepest mysteries of the universe.
The study of quasars and distant galaxies is not merely about looking into the universe's past, but also an ongoing journey to understand its complex evolution. We are gradually piecing together a comprehensive picture of how the universe developed from a hot, dense singularity after the Big Bang into the vast and diverse structure we see today. Observations of quasars help us better understand the parallel development and symbiotic relationship between supermassive black holes and their host galaxies, a relationship believed to be very close, where black holes and galaxies seemingly grow together, influencing each other through energy and matter feedback. However, many big questions remain unanswered and await discovery by future generations of telescopes and scientists. What was the origin of the first seed black holes? Were they the result of the collapse of the first massive stars or other processes? Does the observed rate of quasars and early galaxies truly represent the entire universe at that time? Or are they merely the brightest, most easily detectable portions, creating an observational bias? Are there other types of objects, even more distant and ancient, waiting to be discovered that current technologies cannot yet reach? Telescope technology is constantly improving, promising groundbreaking discoveries. Ground-based telescopes, like the extremely large telescope in Chile, will be able to collect significantly more light than current telescopes, extending our vision to the farthest reaches of space and time. Valuable data from the oldest quasars are helping us refine modern cosmological models, testing hypotheses about dark matter and dark energy, two mysterious components that make up most of the universe but are still poorly understood. For example, the distribution and properties of quasars can be influenced by the distribution of dark matter, which acts as the skeleton for large cosmic structures to form. By comparing observations with predictions from different models, scientists can rule out or confirm theories, gradually bringing us closer to a comprehensive and accurate understanding of the universe.
The journey to explore the early universe is an unceasing intellectual adventure, requiring persistence, creativity, and advanced technology. Each discovered quasar, each distant galaxy whose spectrum is analyzed, is a new page turned in the grand history book of the universe. They are not merely astronomical objects, they are powerful evidence of how the universe forged itself, from an unimaginable starting point to the vast and complex cosmos we inhabit today, and an endless source of inspiration for humanity. From luminous quasars and early galaxies, we have journeyed back in time to witness the dawn of the universe, better understanding the formation of grand cosmic structures. We have seen how light carries ancient stories, revealing the birth of supermassive black holes and the reionization of the universe. But are there other messages, unseen forces shaping the cosmos that we cannot yet perceive with light? In the next episode, we will go beyond what the naked eye can see, delving into the world of gravitational waves and hypergravity. Join us to discover how the slightest ripples in space-time reveal momentous secrets about the most dramatic cosmic events. Don't miss the next journey as we unveil the invisible curtain of the universe.